Hello everyone, and welcome to my talk, SLUBStick, Arbitrary Memory Writes Through Practical Software Cross-Cache Attacks Within the Linux Kernel. SLUBStick is a side-channel supported kernel exploitation technique which presents the following contributions. The first one, it exploits a timing side-channel on the slub allocator to make software cross-cache attacks practical. The second is it presents a primitive conversion which converts a limited heap write to a more controllable use of the free write. And lastly, it uses this more controllable use of the free write to perform page table manipulations to ultimately obtain an arbitrary physical read-write primitive, which is known to be God mode for kernel exploitation. We then implement 9 proof of concepts exploits and provide our artifacts open source. My name is Lukas Maar. I'm a PhD candidate at Graz University of Technology, and my overall goal is to improve system security. Before going into details of SLUBStick, let's start with some background. Here, we see a typical system with, on the left, applications and system services, and on the right, the hardware. In between is the software level, the kernel. When considering the kernel memory allocator, the kernel has simplified 2 kinds of allocators, the body allocator and the slub allocator. Simplified, the body allocator is a page order free list, where each free list has a page order memory free list of page order memory chunks. On top of the body allocator sits the slub allocator, which is basically which provides basically allocation caches with a more fine-grained allocation sizes. When an application requires kernel memory, such as for an object allocation, the object will be allocated via the slub allocator. So the slub allocator returns 1 free and available memory slot for the application. If the application allocates or requires a second object, the slub allocator returns a second object. However, if one allocator cache is empty, so the allocator cache doesn't have any free and available memory slots left, it resorts to the body allocator to allocate one entire memory chunk, which refills all free and available slots within this allocator cache. And subsequently, the slub allocator returns 1 free and available memory slot. The kernel provides, on the high-level perspective, 2 kinds of caches, the generic cache and dedicated caches. Generic or objects from generic caches are allocated via the kmalloc function, where one allocation will be located on an entire memory chunk within the generic cache. So allocation and deallocation might look something like that. If an application allocates from a dedicated cache, like from the file cache, this object will be located on a different memory location. Similar for another dedicated cache, the credential cache. This kind of design provides also security benefits, because imagine if you have a use of the free write from a generic cache, which is where most of the vulnerabilities happens, it's not straightforward to convert this use of the free write to a use of the free write of, let's say, the credential cache. However, security researchers have proposed a way to circumvent this separation, and it's called cross-cache reuse attacks. So for cross-cache reuse attack, an attacker exploits a vulnerability to obtain some kind of write primitive, for example, by exploiting the use of the free. Then the attacker frees all the generic objects within the memory chunk of the generic cache. Hence, the kernel recycles the entire memory chunk. In the next step, the attacker reclaims this memory chunk for sensitive objects, in our case, the credential struct, or credential structs. And lastly, the attacker triggers the write primitive to now, instead of overwriting the generic object, overwrite sensitive data. In the past, these kind of attacks mainly occurred on dedicated caches because cross-cache attacks on dedicated caches is significantly more reliable because a dedicated cache has typically only one allocation site, while generic caches has a lot of allocation site with sometimes order of thousands. There are some cross-cache attacks on generic caches, however, these required stabilization object to perform the cross-cache attack reliably. With the background being done, let's continue with SLUBStick. SLUBStick works simplified in 3 stages. At the first stage, we have a write primitive of a free object on a generic cache. We perform a cross-cache attack that the write primitive now refers to a page table instead of the generic cache. In the next step, we trigger the write primitive to now overwrite the page table entry, which allows us to refer to an arbitrary page in physical memory. To achieve this, there are 3 challenges. The first challenge is, as I previously said, cross-cache attacks on generic caches are pretty unreliable. The second challenge is that most heap vulnerabilities only grants weak write primitives, and we require a write primitive at the attacker-controlled timing as well as an attacker-controlled value. And the third challenge is we only want to trigger this write primitive once, so therefore it's not straightforward from this page manipulation primitive to obtain an arbitrary read-write primitive. To solve the first challenge, we exploit a timing side channel on the SLUB allocator, where we measure the timing on object allocations and group this object in according to the timing. Let's say the first allocation, this will happen directly from the SLUB allocator, therefore the allocation will be pretty fast. The next one is also fast, next one also. Now we are at that point, or at that state where the next allocation will go not to the SLUB allocator, but to the body allocator, which requires significantly more time. So therefore, we observe a very slow allocation time. This indicates that this object is now located on a freshly allocated memory chunk. All the subsequent allocations will be fast because these are again done by the SLUB allocator, till this memory chunk is also, or doesn't also have free and available objects left. Therefore, the next allocation will be slow again. This allows us that, so now we know that all of these left objects are located within one memory chunk. Therefore, we can free all of these objects to prompt the kernel to recycle this memory chunk, and then we reclaim this memory chunk as a page table. We perform some evaluations on different generic caches, on an idle system without CPU pinning and with external noise. And we see that in a lot of cases, we have a success rate of above 99%, where the success rate of prior work might be even as low as 40%. So a very significant increase. Yeah. To solve the second challenge, we want to convert a very limited heap write to a more powerful use of the free write. Initially, we perform this timed allocation, where we now have allocation control over the entire memory chunk of this generic cache. Then we exploit the use of the free vulnerability, where I can go into detail here in the presentation, but the paper explains it in detail. This use of the free then allows us a dangling pointer within one memory slot of the memory chunk. Subsequently, we execute a syscall which internally executes a code pattern similar to replace user TLV. Inside, we reclaim the memory chunk of the dangling pointer, in our case, for a container, where it subsequently executes copy from user space. We provide a user buffer, buff, which causes a page fault which is very slow. There are some kind of methods how to do it. One is to use the fuse, so the file system for user space interface, or we can tweak some kind of, we can perform some other tweaks to perform a very slow page fault. So during this time, we perform our reliable recycling and reclaiming as a page table, and that then after the page fault, it now doesn't overwrite the generic cache, but it overwrites page table entries of our page table. This brings me to solving the third challenge. We manipulate the memory that the write primitive refers to a page upper directory, and then we trigger the write primitive to overwrite entries of the page upper directory. That these corrupted entries now refers to the first gigabyte of the physical memory. We don't need any information leakage because entries do refer to the lowest gigabyte of the physical memory is always the same, independent of some kind of physical KSLR. Then, what we do next, we perform a lot of allocation of page tables until eventually one page table will be located in our first gigabyte of physical memory. The former corrupted page upper directory entry now allows us to overwrite entries of the new allocated page table, the PD prime, which is exactly what our physical read-write primitive is, because via the page upper directory entry prime, we overwrite the page table entry and scan the entire physical memory to find, in our case, the targeted page for etc shadow, so etc password, and then we can overwrite this. We implement 9 proof of concepts exploits which exploit these vulnerabilities and succeeded in privilege escalation of all of them. To conclude this presentation, we presented a timing side channel to make software cross-cache attacks practical. We presented primitive conversions to convert limited heap bytes to more powerful use of the free bytes. We then use this use of the free bytes for page table manipulations to ultimately obtain an arbitrary physical read-write primitive. We implemented 9 proof of concept exploits for the Linux kernel v6.2. Now I'm at the end. Thank you for your attention.